Welcome, everyone. I'm excited to kick off this presentation with you today. Our focus is on sound, a fascinating and vital topic. Today, we'll explore the different aspects of sound, its importance, and how it impacts us all. We'll cover key concepts, some interesting insights, and practical applications. Let's get started and dive into the world of sound together. Sound waves are a type of longitudinal wave, which means that the particles in the medium move back and forth in the same direction as the wave travels. These waves are capable of moving through any type of material medium, whether it's a solid, a liquid, or a gas. The speed at which sound travels isn't the same everywhere. It actually depends on the properties of the medium itself. For example, sound moves faster in solids than in gases, because the particles are more tightly packed and can transfer vibrations more quickly. Understanding how sound waves propagate through different media helps us grasp a lot of practical applications, from acoustic engineering to medical imaging. So, as we move forward, keep in mind that the medium's characteristics are key in determining how sound behaves and how effectively it travels. When sound travels through a medium, what's actually happening is that the particles of that medium vibrate along the same direction as the wave is moving. So, if the wave is moving forward, the particles are oscillating back and forth in that same direction. This is a key characteristic of what we call longitudinal waves. Now, this is quite different from transverse waves, where the particle motion is perpendicular to the direction of wave propagation. For example, think about waves on a string or water waves. Those are transverse because the particles move up and down or side to side, not along the direction the wave is traveling. Understanding this difference helps us grasp how different types of waves behave and how they transfer energy through various media. It's a fundamental concept that connects to the overall theme of wave motion and how energy propagates through different environments. This slide doesn't contain enough information. That's why we're moving to the next slide. So, the displacement that occurs as a result of sound waves involves the longitudinal displacements of individual molecules. Basically, when a sound wave travels through a medium, it causes these molecules to move back and forth along the same direction as the wave is moving. This movement isn't random. It's organized into regions of compression and rarefaction. Compression is where molecules are pushed closer together, creating a high-pressure area. Rarefaction, on the other hand, is where molecules are spread apart, leading to a low-pressure region. These alternating high and low-pressure regions are what we call compression and rarefaction. Now, an important point to remember is that sound waves are classified as longitudinal waves. This means they propagate through all types of media, solid, liquid, or gas, by means of these compressions and rarefactions. It's fascinating because it shows how universal the process is. No matter what medium the sound travels through, the basic mechanism remains the same. Understanding this helps us see the fundamental nature of how sound moves and interacts with different environments, which ties right into the broader theme of how sound waves behave and propagate. This slide doesn't contain enough information. That's why we're moving to the next slide. Sound is a form of energy made by vibrations. When an object vibrates, it causes the air particles around it to move. These particles bump into the particles close to them, creating a chain reaction. This process continues until the energy runs out. The origin of sound lies in these vibrations, which set the air particles in motion. Understanding this helps us see how sound travels through the air and reaches our ears, connecting the idea of energy transfer to everyday experiences with sound. Sound is essentially a variation in the pressure of the air, and this variation has a real effect on our ears and brain. When we hear sound, what's really happening is that there are changes in air pressure that travel through the environment, and our auditory system interprets these changes as sound. Sound can be produced in many different ways. Usually, it happens because of some mechanical disturbance on an object that causes it to vibrate. These vibrations are key because they generate the sound waves that we eventually perceive. For example, think of guitar strings. They vibrate when plucked, creating sound. Or our own vocal cords. they vibrate when we speak or sing. Devices like loudspeakers use vibrations to produce sound waves that we can hear clearly. Jet engines and drums are also great examples. They produce powerful vibrations that generate loud sounds. Understanding these mechanisms is important because it ties into the overall theme of how sound is created and transmitted, which is fundamental to our study of acoustics and sound engineering. Every sound we hear starts with some form of mechanical disturbance causing vibrations, and those vibrations travel through the air as pressure variations, just like we see here. Today, I want to talk about the different types of sound. When we think about sound, it's not just one simple thing. There are actually various kinds that serve different purposes. First, we have ambient sounds, which are the background noises that create the environment around us. Think of the rustling leaves or city traffic. They help set the scene. Then, there are dialogue sounds, which are crucial because they carry the story forward through what characters say. These can be spoken words or any vocal expressions. Next, we have sound effects, which are used to emphasize actions or create a mood, like a door creaking or a thunderclap. Lastly, music plays a vital role, adding emotional depth and atmosphere to a scene. Understanding these different types helps us see how sound can be used creatively and effectively to enhance storytelling. It's all about how these elements work together to immerse the audience and support the overall theme of the presentation. When we wave our hands, we actually produce compressions and rarefactions in the air, which are the fundamental parts of sound waves. But interestingly, we don't hear any sound from just waving our hands because the frequency of those vibrations is too low, less than 20 Hz. This is below the threshold of human hearing, so our auditory nerves don't register it. On the other end of the spectrum, if the vibrations happen at very high frequencies, above 20,000 Hz or 20 kHz, we also don't hear anything. The vibrations are happening so rapidly that our ears simply can't respond to them. This highlights a key point about the limits of human hearing. We only perceive sounds within a certain frequency range, roughly from 20 Hz to 20 kHz. Understanding these boundaries is crucial because it helps us grasp how different sounds are produced and detected, which ties into the broader theme of how sound waves interact with our sensory system. This slide doesn't contain enough information. That's why we're moving to the next slide. Audible waves are sound waves that our human ears can actually hear. The range of human hearing typically spans from 20 Hz up to 20 kHz. In simpler terms, that means we can't hear sound waves that are below 20 Hz or above 20 kHz. These audible sound waves can be produced in many different ways. For example, musical instruments, our own vocal cords, and loudspeakers all generate these sounds. Understanding this range is important because it helps us grasp what sounds are perceivable and how different devices produce the sounds we experience daily. This ties into the overall theme of how sound waves are created, transmitted, and perceived by us. Those waves which human ear cannot hear are called inaudible waves. Now, moving on to inaudible sound waves, these are sounds that have frequencies outside the range of human hearing. Essentially, they are too high or too low for us to perceive. For example, very high-frequency sounds like ultrasonic waves are used in medical imaging, while very low-frequency sounds, like in seismic activities, are inaudible to us. These inaudible waves play important roles in various fields, even though we can't hear them directly. Understanding these waves helps us grasp the full spectrum of sound and wave phenomena beyond just what we can perceive with our ears. Let's talk about infrasonic waves first. These are longitudinal waves with frequencies below 20 Hz. An interesting example of infrasonic waves are earthquake waves, which are generally below the human hearing range, but play a crucial role in how we detect and understand seismic activity. Moving on to ultrasonic waves, these are also longitudinal waves, but their frequencies are well above the human hearing threshold, specifically above 20 kHz. A common example of ultrasonic waves in everyday life is their generation through vibrating quartz crystals. When we apply an alternating electric field to a quartz crystal, it induces vibrations that produce ultrasonic waves. These are used in various applications, from medical imaging to industrial testing. Now let's broaden our understanding of sound itself. Broadly speaking, sound can be classified into two major groups: musical sound and noise. Here, where it gets interesting, whether a sound is considered musical or noise really depends on the listener's perception. For one person, a certain melody might sound beautiful and musical, but for someone else, it may seem like noise. So the distinction between a musical sound and noise is subjective. It's all about personal perception and context. This highlights how diverse our auditory experiences are and reminds us that the way we interpret sound can vary greatly from person to person. Throughout this presentation, this idea of perception ties into the broader theme of how we understand and interpret different types of waves and sound phenomena in our environment. Now let's take a closer look at the characteristics of sound waves. Sound waves are primarily characterized by three main features: pitch, loudness, and quality. Pitch, which we often perceive as how high or low a sound is, depends on the frequency of the wave. The higher the frequency, the higher the pitch. Loudness refers to how intense or powerful a sound feels, and this is related to the amplitude or intensity of the wave. Then there's quality, which is what allows us to distinguish different sounds even if they have the same pitch and loudness. Think about the difference between a guitar and a piano playing the same note. It's also important to understand that the speed at which sound travels isn't the same everywhere. It actually depends on the medium transmitting it. For instance, sound travels faster in solids like metal or glass compared to liquids or gases. This is because the particles are more tightly packed in solids, allowing the sound waves to move through them more quickly. These characteristics are fundamental because they influence how we perceive sound and how sound interacts with different environments. Recognizing these properties helps us better understand everything from how musical instruments produce sound to how sound waves behave in various mediums, tying back to the overall theme of how sound functions in our world. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's explore some key concepts related to waves. First, amplitude. This is essentially the maximum displacement of the medium from its rest position when a wave passes through. Think of it as how tall or how intense the wave is. The larger the amplitude, the more energy the wave carries. We usually denote it by the letter A. Next, we have wavelength. This is the distance between two successive crests or two successive troughs. It tells us about the spatial length of one complete wave cycle. The wavelength is represented by the Greek letter lambda. Understanding wavelength helps us grasp how spread out or compressed the wave is in space. Finally, let's talk about the time period. This is the time it takes for the wave source to complete one full vibration or cycle. If you imagine a single pulse or oscillation, the time it takes to complete that cycle is the time period. We denote it by T. Connecting these ideas, the amplitude relates to the energy, the wavelength to the spatial characteristics, and the time period to the temporal aspect of waves. All of these are fundamental in understanding how waves behave and propagate through different media, tying into the overall theme of wave mechanics and energy transfer. Now let's talk about frequency. The frequency of a wave is essentially how many complete cycles pass a specific point in just 1 second. It's represented by the letter F. To give you a sense of scale, the unit we use for frequency is Hertz, or Hz. An important relationship to remember here is that frequency is the inverse of the period, so F equals 1 divided by T, where T is the time for one cycle. Moving on to wave velocity, this is about how far a wave travels in 1 second. It's called wave velocity and is denoted by V. In the International System of Units, we measure it in meters per second, or ms. Understanding wave velocity is crucial because it ties together how quickly a wave moves with its frequency and wavelength, helping us get a complete picture of wave behavior. By grasping these concepts, we're building a solid foundation for understanding how waves propagate through different media and how their properties are interconnected. Let's start with vibration. Vibration is basically any regularly repeated to and fro motion or change. You can think of it as something oscillating back and forth in a consistent pattern. This concept is really important because vibrations are everywhere, from the engines of machines to the strings of a guitar. Understanding vibration helps us analyze and control mechanical systems better. Now, moving on to phase. Phase refers to the specific stage in a cycle that a wave has reached at a particular moment, relative to some reference point. Think of it like a snapshot of where a wave is in its oscillation at a given time. If you imagine a wave cycle as a clock, the phase tells you what time it is on that clock. Both vibration and phase are fundamental to understanding how waves behave and interact. They tie into the larger theme of wave dynamics, which is crucial in fields like acoustics, electronics, and mechanical engineering. Recognizing these concepts helps us predict how systems respond and how to optimize their performance. A sound wave is fundamentally a pressure disturbance that propagates through a medium by particle interaction. In other words, when a sound wave moves through a medium, it causes particles to alternately contract and expand, creating a wave that travels through the medium. This process relies on the particles interacting with each other, transmitting the energy from one to the next. The speed at which these sound waves travel through the medium is called the speed of sound. Understanding this concept is key because it helps us grasp how sound moves through different materials, which is a central theme in our overall exploration of acoustics and wave behavior. The velocity of sound depends on the properties of the medium, such as density and elasticity, which we'll delve into further as we continue. The velocity of sound, simply put, is the distance that a sound wave's point, like a compression or a rarefaction, travels in a certain amount of time. It's a key concept because it helps us understand how fast sound moves through different media. To find this velocity, we use a specific formula. V equals lambda times F here. V stands for the velocity of sound, lambda is the wavelength of the sound wave, and F is its frequency. What this means is that the speed of sound depends on both the wavelength and how often the wave oscillates. Longer wavelengths or higher frequencies will affect how quickly the sound travels. Connecting this to the broader theme, understanding the velocity helps us grasp how sound behaves in various environments, whether it's in air, water, or solids. It's fundamental for everything from acoustics to designing better audio systems. Sound is essentially a disturbance, a kind of ripple that travels through a medium. It happens because particles collide with each other, passing on that energy from one molecule to the next. Now, when we look at the different states of matter, solids stand out because they are much denser than liquids or gases. That means in solids, the molecules are packed much closer together. This proximity is really important because it allows the molecules to collide very quickly. So, in solids, sound can travel faster because these collisions happen more frequently. This idea of density and molecular closeness helps us understand why sound moves differently through solids compared to other states, and it ties back to our overall theme of how particles interact to propagate various phenomena. Effectively, it takes less time for a molecule of a solid to bump into its neighboring molecule compared to other states of matter. This quicker interaction is a key reason why the velocity of sound in solids is faster than in gases. For example, in general, the speed of sound in a solid can be around 6,000 meters per second. To put that into perspective, in steel, which is a common solid material, the speed of sound is about 5,100 meters per second. Now, here's an even more fascinating fact. Sound travels approximately 35 times faster in diamonds than it does in air. That's because the atomic structure of diamonds allows vibrations to pass through much more efficiently. This highlights how the properties of the material directly influence how quickly sound waves can travel through it, which ties back to our overall theme of understanding wave propagation and material characteristics. Similarly, the density of a liquid is greater than the density of a gas. So, when we compare these states of matter, we see that liquids are much more dense than gases. Now, because of this increased density, the distances between molecules in liquids are smaller than in gases, but still larger than in solids. This means that in a liquid, molecules are packed closer together than in a gas, but not as tightly as in a solid. And this arrangement has a direct impact on how sound travels through these mediums. Since the molecules are more closely packed than in gases, the speed of sound in liquids is faster than in gases, but slower than in solids. So, if we think about the overall picture, the speed of sound in liquids falls somewhere in the middle. It's higher than in gases, but lower than in solids. This concept of molecular density and spacing really helps us understand why sound propagates differently across various states of matter, connecting to our broader discussion on how physical properties influence wave behavior. The speed of sound in water is actually faster than in air, which is quite interesting when you think about it. In water, sound travels at approximately 1480 meters per second, making it much quicker than in the air. This difference is really important, especially when we consider underwater communication or sonar technology. It's also fascinating to note that the speed can vary slightly. In distilled water, for example, it can range from about 1450 to 1498 meters per second. These small differences depend on factors like temperature and purity of the water. Now, when we look at seawater, the speed increases to around 1531 meters per second, particularly when the temperature is between 20 and 25 degrees Celsius. This variation shows how temperature and salinity can influence how fast sound travels underwater. All these points highlight how the environment plays a crucial role in sound propagation, which is a key aspect when we study underwater acoustics and marine communication systems. Now, when we talk about gases or air, it's important to remember that gases tend to expand to fill whatever space they're in. Because of this, their density remains relatively uniform, regardless of the specific type of gas. This is quite different from solids and liquids, where density can vary more significantly. Another key point is that the density of a gas isn't affected by the frequency of the sound wave or the pressure and density of the medium itself. However, it's crucial to note that none of the gases we encounter in everyday life are truly ideal gases. Real gases deviate slightly from the ideal behavior, which can cause small variations in their properties. Now, focusing on the velocity of sound in air, at room temperature, around 20 degrees Celsius, it averages about 343.2 meters per second. To put that into perspective, that's roughly 1,236 kilometers per hour. This high speed of sound in air is a fascinating aspect, especially when considering how sound travels through our environment. So, understanding these properties helps us see how sound propagates through gases and why their behavior is predictable, yet subtly influenced by real-world conditions. When the pressure of a given amount of gas changes, we see a corresponding change in its volume and density. Essentially, if the temperature stays constant, Boyle's law tells us that pressure and volume are inversely related. So, if you increase the pressure, the volume decreases, and vice versa. This relationship is fundamental because it helps us understand how gases behave under different conditions. Now, connecting this to the overall theme, it's important to recognize that pressure, along with temperature and humidity, significantly influences the speed at which sound travels through the air. Changes in pressure can alter the density of the air, which in turn affects sound propagation. So, understanding these relationships isn't just about gases. They're key to grasping how sound moves through different atmospheric conditions. Alright, so in this slide, we're looking at Newton's formula and the assumptions behind it. Newton considered the way sound waves move through air and assumed that this process is isothermal. That means the temperature of the air stays constant during the propagation of these sound waves. He argued that when air gets compressed, a tiny amount of heat is generated, but this heat doesn't stick around. Instead, it's quickly carried away to the areas where the air is expanding or rarefying, causing a slight cooling there. This rapid heat transfer ensures that the temperature of the gas remains unchanged throughout the process. And here's the key point. Because the temperature stays constant, the pressure and volume of a given amount of gas are related by Boyle's law, which states that pressure times volume is a constant. So, for any fixed mass of air, if we know the pressure and volume, We can understand how sound propagates by assuming this isothermal behavior. This assumption simplifies the analysis and ties directly into the overall theme of understanding wave behavior in gases. Let's talk about Laplace's formula now. Laplace pointed out something quite interesting about how sound waves travel through air. He argued that this process isn't actually isothermal, which means constant temperature, as Newton suggested. Instead, it's an adiabatic process, meaning there's no heat transfer happening during the wave propagation. Why is that? Well, Laplace explained that because compressions and rarefactions in sound waves happen very quickly, there isn't enough time for heat to flow from one region to another. Think of it this way. When air compresses, its temperature slightly rises, but because this happens so rapidly, heat doesn't escape to the surrounding air. Similarly, in the rarefaction zones, the temperature drops slightly, but again, there's no significant heat flow to balance it out. He also pointed out that these regions, compressions and rarefactions, are separated by quite large distances relative to the speed of the wave. And since the temperature differences are small and the process happens so fast, there's no appreciable heat flow from the warmer compression zones to the cooler rarefaction zones. Connecting this to the overall theme, understanding that sound propagation is an adiabatic process helps us better grasp the physics behind sound waves. It explains why temperature changes are localized and why heat transfer doesn't play a significant role during wave travel. This insight from Laplace is fundamental in accurately modeling sound behavior in air. So, if the temperature of the gas stays constant, the speed of sound in that gas also remains unchanged, even if the pressure varies. This is an important point because it shows that pressure alone doesn't directly affect the speed of sound, provided the temperature is steady. Now, the relationship between pressure and volume of air in these conditions is described by what's called the adiabatic relation. Essentially, this tells us how pressure and volume are connected when no heat is exchanged with the surroundings. This concept ties into our overall theme of understanding how gases behave under different conditions, especially in acoustic phenomena. When the temperature of a gas changes, its density also changes, but interestingly, the pressure remains unaffected. This means that as the gas gets warmer or cooler, its density shifts accordingly, and this has a direct impact on the speed of sound traveling through it. So, the key point here is that the speed of sound doesn't stay constant. It varies with temperature. In fact, the speed of sound is directly proportional to the absolute temperature of the gas. As the temperature increases, the molecules move faster, and sound travels quicker. Conversely, at lower temperatures, the speed decreases. This relationship is crucial because it links temperature directly to how sound propagates through gases, which is an important aspect when considering acoustic properties in different environments. So, overall, understanding this effect helps us see how temperature influences sound transmission, fitting into the broader theme of how physical conditions impact acoustic behavior. When we look at the effect of wind on sound, it's really about the direction of the wind. If the wind blows in the same direction as the sound, then the velocity of the sound actually increases. It's like the wind is helping push the sound along, making it travel faster. But if the wind blows against the sound, in the opposite direction, then the velocity decreases because the wind is kind of fighting against the sound's movement. So, wind direction plays a crucial role in how quickly sound travels. Now, moving on to the effect of frequency, or what we often call pitch. Interestingly, the frequency doesn't really affect the speed at which sound travels through a medium. Whether you're dealing with high-frequency sounds like a whistle or low-frequency sounds like a drum, they all tend to move at the same speed in air. The key difference is in their wavelength. Higher-frequency sounds have shorter wavelengths, and lower-frequency sounds have longer ones. But no matter the frequency, the speed remains consistent in a given medium, which is an important point to remember when studying sound propagation. Connecting this to the overall theme, understanding these factors helps us grasp how sound behaves in different environments. Wind can either facilitate or hinder sound travel depending on its direction, and frequency doesn't alter the speed, just the wavelength. This knowledge is fundamental in fields like acoustics and audio engineering, where controlling sound transmission is crucial. Now, when we consider low temperature and pressure conditions, the density of water vapor is actually less than that of air. This means that when moisture is present in the same volume of air, it effectively reduces the overall density of the mixture. And as you might recall from earlier, the speed of sound is influenced by the medium's density. So, with the presence of humidity, the density decreases, and this causes the speed of sound to increase. In other words, more humid air allows sound waves to travel faster. This is a key point because it links humidity directly to how sound propagates through the atmosphere, which ties into our broader discussion on environmental effects on sound transmission. Now let's talk about reflection. Just like light, sound also reflects when it encounters a surface. The fascinating part is that it follows similar laws as light reflection. Specifically, the angle at which sound hits a surface, the incident angle, is equal to the angle at which it bounces off, the reflected angle. And importantly, both the incident sound, the reflected sound, and the normal line to the surface all lie in the same plane. Sound reflection occurs when sound waves bounce off surfaces, which can be made of solids or liquids. This bouncing effect influences how sound propagates in different environments, affecting things like echo and reverberation. Understanding reflection, along with refraction and acoustic impedance, is key to grasping how sound behaves in various mediums. These concepts are fundamental in fields like acoustics design, audio engineering, and even medical imaging. So, in essence, reflection is about how sound waves change direction after hitting a surface, governed by these consistent physical laws. It's a crucial part of understanding how sound interacts with the environment around us. The angle of reflection is always equal to the angle of incidence. This means that when sound hits a surface and bounces off, the angle at which it arrives, the incidence angle, is the same as the angle at which it leaves, the reflection angle. It's a fundamental principle that helps us understand how sound behaves when it encounters reflective surfaces. Additionally, the reflected sound, the incident sound, and the normal, think of the normal as an imaginary line perpendicular to the surface, all lie in the same plane. This is important because it shows that the reflection occurs within a single, predictable plane, which helps us analyze and predict sound paths more accurately. These laws of reflection are crucial because they form the basis for understanding sound behavior in various environments, whether we're designing concert halls, auditoriums, or even trying to control echoes in a room. Recognizing these principles allows us to manipulate sound reflections to improve acoustics or reduce unwanted noise, tying directly into the overall theme of understanding sound behavior in different settings. Let's talk about echoes, which are a fascinating application of sound reflection. An echo occurs when sound waves bounce off a surface and come back to us, creating a repeated sound. You'll notice that the echo arrives after the original sound, and there's usually a delay. Now, if this delay is longer than 1/10 of a second, we call it an echo. This delay is key because it helps us distinguish an echo from other sound reflections. Echoes are not just interesting. They have practical uses in areas like sonar and even in architecture to understand how sound travels in different spaces. So, understanding how sound reflects and creates echoes helps us better understand sound behavior in various environments. Bats and dolphins are fascinating examples of animals that use echo to navigate their environment. They emit sounds that bounce off objects, and then listen for the echoes to detect obstacles around them. This natural sonar helps them avoid collisions and hunt effectively, even in complete darkness. Echo is not just a biological tool, it's also a key technology called sonar, which stands for sound navigation and ranging. Sonar uses the same basic principle, sending out sound pulses and listening for the echoes to locate and identify objects underwater. This technology is crucial for detecting submerged objects like submarines or icebergs, which are often hidden from view. By analyzing the returning echoes, ships and submarines can determine the size, shape, and distance of these underwater obstacles. So, whether in nature or technology, echo-based detection allows us to see and navigate through environments that are otherwise inaccessible or hidden from our eyes. It's a perfect example of how understanding biological systems can inspire and improve our technological solutions. An echo is heard only if the distance between the person producing the sound and the rigid obstacle or reflector is long enough to allow the reflected sound to reach the person at least 0.1 seconds after the original sound is heard. Now, this 0.1 second delay is crucial because it helps us distinguish the echo from the direct sound. For us to perceive a clear echo, the minimum distance in air between the sound source and the reflector needs to be about 17 meters. That's quite a distance. Think of a large hall or an open space where sound can bounce back effectively. Another important point is that the intensity of the sound must be strong enough so that, when it reflects, the sound reaching our ears is still loud enough to be heard clearly. If the reflected sound is too faint, we won't perceive it as an echo, no matter how far the obstacle is. So, in summary, for a distinct echo, the reflector has to be at least 17 meters away, and the sound must be loud enough to be audible after reflection. These conditions are essential for understanding how echoes work, especially in applications like sonar or acoustic design. Now, let's look at hearing aids. A hearing aid is a device designed for people who have difficulty hearing. It works by receiving sound waves from the environment. These sound waves are then reflected within the device, which helps to direct them in a narrower area toward the ear. This focused reflection enhances the clarity of the sound, making it easier for the wearer to understand speech and other sounds. Moving on to the megaphone, which is quite different but also plays a crucial role in sound amplification. A megaphone is a horn-shaped tube that helps project sound over a distance. It works by preventing the spreading out of sound waves through successive reflections inside the horn. Essentially, these reflections confine the sound waves within the tube, directing them outward in a focused manner. Both of these devices, hearing aids and megaphones, are great examples of how we can manipulate sound waves to improve hearing or amplify our voice, fitting into the broader theme of understanding and controlling sound propagation. The speed of a wave, including sound, depends heavily on the properties of the medium it travels through. When a wave moves from one medium to another where the wave speed is different, it doesn't just keep going straight, it actually changes direction. This change in direction is what we call refraction. Specifically for sound, the speed in air varies with temperature. As the temperature increases, the molecules move faster, which typically causes the sound to travel faster. Conversely, in cooler air, sound slows down. Most of the time, when we see refraction of sound, it's due to variations in local temperature. These temperature differences cause changes in the wave's speed, leading to the bending or refraction of the sound wave. Understanding this helps us grasp how sound behaves in real-world environments, especially under conditions where temperature gradients are present. This concept ties into the overall theme of how waves interact with their surroundings and how properties of the medium influence wave behavior. So during the day, the air is actually warmest right next to the ground, and as you go higher up, it gets cooler. This pattern is known as a temperature lapse. Now, because temperature decreases with height, it also affects the speed of sound. Specifically, the speed of sound decreases as you go higher. What this means is that if you imagine a sound wave traveling close to the ground, the part of the wave that's near the ground is actually moving faster. Conversely, the part of the wave that's higher above the ground moves more slowly. This difference in speed can impact how sound travels through the atmosphere, especially near the surface where these temperature variations are most pronounced. Understanding this concept helps us see why sound behaves the way it does in different atmospheric conditions, which ties back to the overall theme of how environmental factors influence sound propagation. A temperature inversion occurs when, instead of getting colder as you go higher, the temperature actually becomes warmer. So, right next to the ground, the air is the coolest, and as you increase in height, the temperature starts to rise. This is a bit counterintuitive because we usually expect it to get colder the higher you go. Now, because the temperature increases with height during an inversion, the speed of sound also increases as you go higher. Think of it this way: sound travels faster in warmer air. So in this situation, the upper layers of the atmosphere are allowing sound waves to move more quickly than those closer to the ground. This difference in speed has interesting effects on how sound travels near the ground. The part of the sound wave that's close to the ground is moving the slowest, while the part that's higher up is moving faster. That means the wave's shape can be affected, often bending or refracting away from the ground, which impacts how we hear sounds, especially over long distances. Understanding this helps us see how temperature inversions influence sound propagation, tying into our broader theme of how atmospheric conditions shape acoustic behavior. When sound waves travel through a medium, like air, water, or solid materials, their energy doesn't stay the same. Instead, it gradually lessens as the distance from the source increases. This process is called attenuation of sound. It's a natural phenomenon where the intensity of sound diminishes with distance, which is important to understand in many applications, from acoustics to communication systems. So, as sound moves farther away, it becomes quieter, and this reduction in strength is a key factor in how we perceive sound at different distances. Recognizing this helps us design better audio equipment and understand environmental sound behavior more accurately. Let's talk about absorption. Absorption is essentially when sound energy is transformed into other forms of energy, like heat. This process reduces the energy of the sound as it travels through a medium. Now, when we consider both scattering and absorption together, we refer to this combined effect as attenuation. Attenuation describes how sound intensity diminishes over distance or as it interacts with different materials. Focusing on scattering, this is when sound waves bounce off surfaces or particles and change direction, rather than continuing straight ahead. It's like when you shout in a forest, and the sound reflects off the trees in various directions. This scattering affects how sound propagates through an environment, influencing clarity and reach. Understanding these processes, absorption, scattering, and attenuation, is crucial because they all impact how sound behaves in different settings, whether it's in designing auditoriums, radio communication, or noise control. They're all interconnected pieces of the bigger picture of sound propagation we're exploring in this presentation. Acoustic impedance is essentially the opposition that a medium offers to the motion of a longitudinal wave. It's a way to understand how sound pressure and particle velocity relate to each other within that medium. When I talk about acoustic impedance, I'm referring to the specific acoustic impedance of the medium itself, which tells us about its inherent properties. Now, when a sound source delivers energy into a medium, the medium doesn't just passively accept it. It resists or opposes that movement. This opposition isn't just a fixed value. It depends on the medium's characteristics, but also on the size of the air mass being pushed by the sound source. So, in essence, acoustic impedance helps us understand how effectively sound energy is transferred between the source and the medium, and it plays a crucial role in many applications, from designing better microphones to understanding how sound travels through different environments. It's a key concept that ties into the overall theme of how sound interacts with various media. When two or more waves of sound with the same frequency are traveling in nearly the same direction, they can meet and superimpose. Now, this superposition isn't just a simple addition. It actually affects the overall intensity of the sound in that region. In fact, the resulting intensity can be quite different from what you would expect if you just added up the individual wave intensities. This phenomenon is known as interference of sound waves. It's a key concept because it explains how sound waves can reinforce each other or cancel each other out, leading to phenomena like loud spots or silent zones. Understanding interference helps us grasp how sound behaves in complex environments, which ties into the broader theme of wave behavior and wave interactions. Now, let's talk about what happens when sound waves overlap in a region. The change in the distribution of sound intensity during this superposition is called interference. Essentially, interference describes how sound waves interact with each other when they meet. Depending on how these waves combine, we observe two main types of interference: constructive and destructive. Constructive interference occurs when waves add up to produce a louder sound, while destructive interference happens when waves cancel each other out, resulting in a quieter or even null sound. Understanding these concepts is key because they help explain many phenomena in acoustics, from the way we hear sound in different environments to the design of auditoriums and soundproofing. So, in the context of our overall discussion on wave behavior, interference is a fundamental principle that shows how waves can influence each other, creating the rich and complex soundscapes we experience. Constructive interference occurs when two waves are traveling in the same direction and they overlap. When this happens, their crests and troughs combine, resulting in a larger wave. This process is what we call constructive interference. In the case of sound waves, when two waves reinforce each other through constructive interference, the resulting sound is louder. So, in everyday life, if two sound sources produce waves that overlap constructively, you'll perceive a louder sound. This concept is important because it shows how waves can interact to create noticeable effects, whether in sound, light, or other types of waves. Understanding constructive interference helps us grasp how various phenomena, like amplifications or loud sounds, occur naturally or in engineered systems. Now, let's talk about destructive interference. This occurs when two waves are traveling in the same direction, but their peaks and troughs are misaligned. Specifically, destructive interference happens when a crest of one wave lines up with the trough of the other. This alignment causes the waves to cancel each other out to some extent, reducing the overall amplitude. We call this phenomenon destructive interference because it essentially diminishes the wave's energy. Understanding this concept is key because it helps explain how waves can interact in various contexts, from sound waves to light waves, and how these interactions influence the behavior of waves in different environments. It's an important piece of the puzzle in understanding wave behavior and interference patterns overall. In destructive interference, two waves meet in such a way that they cancel each other out. This means that their effects effectively reduce each other, leading to a decrease in overall wave amplitude. When this happens with sound waves, for example, we can't hear the sound properly or the sound intensity diminishes significantly. This interplay is a key part of the broader phenomenon of interference, where waves can either amplify or weaken each other. So, due to interference, we observe maximum sound levels, which we call constructive interference, and minimum sound levels, known as destructive interference. The minimum sound, or null sound, is when the waves cancel each other out completely, resulting in silence or a very faint sound. Understanding these concepts helps us grasp how waves interact in various environments, which is fundamental in fields like acoustics, optics, and even wireless communications. It's fascinating how the same wave principles can produce such contrasting effects, louder sounds in one instance and complete silence in another, showing the power of interference at work. When a source generating a wave moves relative to an observer, or when an observer moves relative to a source, there is an apparent shift in frequency. This means that the frequency we perceive can change depending on whether the source or the observer is in motion. This phenomenon is known as the Doppler effect. It's named after Christian Doppler, an Austrian physicist from the 19th century, who first explained this interesting behavior. The Doppler effect is a key concept because it helps us understand how waves, like sound or light, behave in different relative motions, and it connects directly to our broader discussion about wave phenomena and how motion influences what we observe. The Doppler effect occurs for all types of waves, whether they are sound waves, light waves, or any other kind. It happens whenever there is relative motion between the source of the waves and the observer. So, if the source of the wave is moving toward you, you'll observe a change in the wave's frequency. Conversely, if it's moving away, the frequency appears to decrease. Now, an important point to remember is that the faster the source is moving, the more pronounced the Doppler effect becomes. This means the greater the speed of the source relative to the observer, the larger the shift in the observed frequency. And just to clarify a common misconception, what we're describing here is the shift in frequency, not loudness. The change in loudness or amplitude isn't what we call the Doppler effect. Instead, it's the change in the perceived frequency of the wave caused by the relative motion. So, understanding this concept helps us see how motion influences wave perception across different contexts, tying into the broader theme of how waves behave in our universe. This slide doesn't contain enough information. That's why we're moving to the next slide. The Doppler effect occurs when a source of waves moves relative to the observer, and a classic example of this is the rise and then the drop in pitch of an automobile horn as it approaches and then passes by. Essentially, what happens is that when the sound source, like a car, moves toward you, the frequency of the sound you hear is higher. As it moves away, that frequency drops. This is because, when the car approaches a stationary listener, the sound waves are compressed, which causes the wavelength to get shorter and the frequency to increase. That's why the pitch sounds higher. Once the car passes and starts moving away, the sound waves spread out, increasing the wavelength and decreasing the frequency you perceive. This simple yet fascinating effect highlights how motion influences wave behavior, and it ties into the overall theme of how waves interact with their environment. Understanding this helps us grasp many real-world phenomena, from sirens to radar and beyond. Let's take a closer look at this slide. As you can see, the letter B is highlighted here, which is central to our discussion. Now, following that, we have the letter A, which ties into the main concept we're exploring today. The indentation of a beneath B indicates a relationship or hierarchy, emphasizing that it is a subset or a specific aspect of B. This visual helps illustrate how different components or ideas are connected within the broader framework. It's important to recognize how these relationships mirror the overall theme of our presentation, understanding the interconnectedness of different elements in a system. By focusing on these key points, we're better equipped to see how each part influences the whole, and how a clear grasp of these connections can lead to more effective strategies and solutions. So, as we move forward, keep in mind how these relationships play a crucial role in the bigger picture we're trying to build. Echo. So, when we talk about echo, we're referring to how sound waves bounce back after hitting surfaces, creating that repeating effect we often hear in canyons or empty halls. It's a fascinating phenomenon because it shows us how our environment influences sound. Echoes are not just about loudness. They also help us understand space and acoustics. In the context of our overall theme, which is about optimizing sound environments, recognizing how echoes work is crucial. It allows us to design spaces that either minimize unwanted echoes or harness them creatively. So remember, echo isn't just a sound effect. It's a key factor in how we perceive and interact with our surroundings. The word echo actually comes from the Greek word, which is quite interesting because it shows the long history behind this phenomenon. In the context of audio processing and acoustics, an echo is essentially a reflection of sound that arrives at the listener's ear sometime after the direct sound. What this means is that when you make a sound, like calling out in a canyon or inside a big hall, some of that sound bounces off surfaces and comes back to you. Typical examples of echoes include those produced when you shout down a well, or when sound hits a building or the walls of an enclosed room, especially if the room is large or empty. These are familiar situations where echoes are quite noticeable. Now, it's important to understand what distinguishes a true echo from other acoustic phenomena. A true echo involves a single reflection of the sound source, meaning the sound bounces back once before reaching your ear. This is different from reverberation, which is multiple reflections blending together. Recognizing this helps us better understand how sound behaves in different environments, which is crucial for fields like acoustics, sound design, and even audio processing. Connecting this to the overall theme, understanding echoes gives us insight into how sound waves interact with our environment, which is essential for improving sound quality in various applications, from concert halls to audio recording. When so many reflections arrive at a listener that they become indistinguishable from each other, we call that reverberation. Essentially, it's a dense, overlapping series of echoes that blend together. On the other hand, echoes are more isolated reflections that bounce off surfaces like walls or mountains, creating a clear, distinct sound. Recognizing the difference between reverberation and echoes is important because it helps us understand how sound behaves in different environments. Whether we're designing concert halls or analyzing natural landscapes, these concepts are key to controlling and interpreting sound. When a vibrating object creates air vibrations in space, the strength of these vibrations varies depending on the frequency. Sometimes, the vibrations are very weak at certain frequencies, and other times they become much stronger. The frequencies at which the vibrations are particularly strong are called resonant frequencies of the system. This phenomenon, where energy builds up at specific frequencies, is known as resonance. Resonance is a key concept because it explains why some sounds are amplified naturally in certain environments or structures. Understanding resonance helps us see how vibrations and sound behave in real-world systems, tying into the broader themes of acoustics and sound engineering. The phenomenon of making a body vibrate with its natural frequency under the influence of another vibrating body with the same frequency is called resonance. Now, what's really interesting about resonance is how it occurs when two objects share the same vibrational frequency. When one object vibrates at its natural frequency, and another nearby object vibrates at that same frequency, the first object can start to vibrate more strongly without any additional force. This process can lead to significant amplification of vibrations. Resonance is a key concept that connects to many areas, from musical instruments to engineering structures. It helps us understand how energy transfer happens efficiently when frequencies match, which is essential for designing safe buildings, musical instruments, and even understanding natural phenomena. Let's take a closer look at the Fresnel and Fraunhofer zones in ultrasound. These zones are crucial for understanding how ultrasound waves behave as they travel through tissue. The Fresnel zone, often called the near field, is the area close to the transducer where the sound waves are still converging and haven't fully formed into a stable beam. In this zone, the intensity of the ultrasound varies, and the beam can be quite complex. As we move further away, we enter the Fraunhofer zone, or the far field, where the beam becomes more uniform and spreads out in a predictable way. Recognizing these zones helps us optimize image quality, since different regions of the tissue are best visualized depending on the zone we're in. Overall, understanding these zones is fundamental for effective ultrasound imaging and ensuring we get the clearest, most accurate results. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. You know, I just want to take a moment to thank you all for your time and attention throughout this presentation. I truly appreciate your engagement and interest. It's been great sharing these insights with you, and I hope you found the information valuable and inspiring. Remember, the key points we discussed today are all about how we can apply these concepts to make a real difference. Connecting these ideas to our overall theme of growth and innovation is what really drives the message home. So, thank you once again for being a part of this journey. Your commitment to learning and improvement is what makes all of this worthwhile.